Okay, finally we can look to our big summaries or our big overview for our electrophilic addition reactions. So we're looking at an alkene, and this is a nucleophilic nonpolar pi bond. Okay, because it has a source of electrons, it's going to react with an electrophilic atom, and that is going to result in the loss of a pi bond. As we break that pi bond, though, so as these electrons come out to react with an electrophile, that electrophile is then going to be associated for one of those carbons. Let's just say that carbon. What happens to the other carbon? Well, the other carbon is going to become partially positive, okay, or formally positive if the reaction happens this way, which means this single starting material has both an electrophilic site and a nucleophilic site, okay, or nucleophilic basic site, electrophilic, not acidic, or an electrophilic site. So because that single molecule has those two chemistries, when we're running through our reactions, we have to ensure that our reagents have the chemistry to be able to neutralize both of those points. Okay, and so when we look at the overarching reaction, it's showing Lewis acid and Lewis base. Why is it going with the Lewis definition and not, say, acid and base? Because we had that potential for it to act, our alkene to act as a nucleophile or a base. So we're shifting to the Lewis acid base to broaden the definition and allowing us to better look at the overall reaction. When we're looking at our particular textbook, Carty divides this up into looking at it as an electrophilic addition with acids or an electrophilic addition with, electrophiles. It's a little bit odd to reference the electrophilic addition with an acid, but that's how Carty is referencing it. We're really saying that that H is an electrophile, which I think what he's trying to do is say that this is really the Lewis acid, and we're doing a Lewis acid reaction, where that Lewis acid is more particularly a hydrogen, which means that we're looking at a Bronsted-Lowry acid. Okay? And then he shifts to chapter 12, where now when we run that reaction, it's reacting very specifically with the electrophile, not a hydrogen. Okay? Both of these cases require relatively strong things. So we're going to need strong acids in chapter 11, and we're going to need good electrophiles in chapter 12 to force those reactions to occur. We get the same basic patterns behind these. If we go through and look, the purple atom is connected to the least substituted position, and the nucleophile is connected to the most substituted position, okay, in both mechanistic styles. So if we can understand those basic patterns, or simple patterns, we can get a better understanding of how these reactions are working and hopefully be able to draw the parallels between them so that we don't have to memorize two different things. We're really just recognizing the pattern and just applying that pattern again and again and again. Okay? So, pi orbital electrons, or p orbital electrons, are higher in energy and therefore more reactions. So more reactive. So what we're seeing is those electrons being the ones to react. And what becomes tricky is that while those electrons are reactive, they are found in a bond connecting two carbons. So those electrons are going to end up with one of those carbons. Well, which one is going to win out? Which one gets that carbon? And so that's where we're referencing in here, is considering the balance of that structure via resonance. So take a second to go through and draw some resonance structures for this. So to give you a little better idea, because maybe it's overlapping too much and you can't pick it out, but what we're looking at is this structure. I want you to go through and draw some resonance structures. So yes, please pause and draw out some resonance. So if we were to do resonance, we could have the electrons from that pi bond go to that carbon, in which case we would be forming a lone pair on that carbon and a negative charge. The other carbon will have lost electrons and now become positive. What happens if we say took the electrons and went the other direction? For the record, by the way, I'm showing two mechanistic arrows doing different things on the same structure. You are not allowed to do this. We're doing it as a simplified fashion to help us get through to these structures. Or we'd have our electrons and to the left carbon and the positive charge. Okay, so those are the two resonance structures. Drawn prettier, we've got these, red versus blue. Which one should we have react with our electrophile? Because if we go through and run our reaction with our electrophile, we'd either attach the electrophile to the negative, because our electrophiles are partially positive or formally positive, or we attach it over here. So where our electrophile goes is going to be dictated based off of the characteristics of our starting alkene. And so if we understand something about that alkene, we can predict the regiochemistry, where the electrophile will go. Okay? How do we decide that? Well, if you've already memorized the previous slide, we actually already said where the electrophile goes. The electrophile goes to the least substituted position, which means in this particular drawing, the red structure was apparently the better structure, okay, or the more likely structure to react. Well, why? Okay. Did I say red structure? I meant blue structure. The blue structure is the important one. Okay. So why is the blue structure better than the red structure? Okay, well, if we want to understand something about reactivity, it's usually best to look at our first worst resonance structure. So where we started was our best resonance structure, where it showed the full pi bond. So what we can do is look at the first worst resonance structure, and in that first worst, we want to shuttle the electrons to the place that's going to stabilize them the best. Again, the nuance issue here, both of them are carbons. Which one prefers the electrons? Well, to answer that, what we'd have to do is look at where is an anion more stable. Okay? Because we talked about that now multiple times. We talked about it in mass spec, and we also talked about it in our reactivity section. The anion is reactive because it has too much electrons. So if I put it near more electrons, it's going to make it more reactive. If we look at the blue structure, we're putting it near hydrogens. If we look at the red structure, we're putting it near carbons. Carbon has more electrons than hydrogen. The anion is better on the least substituted position. And for those of you screaming, well, but the cation, okay, well, let's look at the cation. The cation's a little bit different. It is reactive because it is missing electrons. So what's going to make it more stable? Well, if we put more electrons near it, it becomes more stable. And when we go through and look at the cation, it's near more carbons in the red structure than it is near the blue structure. Again, the blue structure is the more stable one. So the blue structure ends up being what I've been calling the first worst, which is a horrible phrase, but as long as we understand what we're talking about, we're okay. So as soon as we have that resonance in mind, we now know where our reactivity is, and we can now push to start placing atoms according to that reactivity. And that's one of the powerful things of dealing with resonance. Okay. So to keep in mind, while we may be showing this formal negative charge, the alkene is still a weak nucleophile. Okay, I know when we looked at the previous chapter, we were like chloride, negative, strong nucleophile. Hydroxide, negative, strong nucleophile. So we see a negative, it's strong. We're like, there's a negative right here. There's a negative in the resonance structure, which means it's not a strong nucleophile. Okay, we'd be looking at our starting material. The starting material does not have that negative charge, so it is not a strong nucleophile, which does mean that we need a strong electrophilic species or strong acids to force this to occur. Okay, we will be addressing that in detail and kind of subtle nuances and let you self-discover that in a little bit. Okay, so first and foremost, let's jump to pi bonds as bases. So if we're going through and looking at this in our simplest form, we have an acid-base reaction-ish first, which is technically wrong, and we'll look at why it's wrong here in a second. Okay, but we're just adding a hydrogen, and then we follow that up with a coordination mechanistic step. How do I know it's a coordination? Because we have that negative charge now just forming the bond with the positive. Okay, and so this will break into two steps, and we'll look at why it needs two steps here in a second too. Do I want to do that first? No, we're going to explain why it's not an acid-base step. Okay, yes, it is the transfer of a hydrogen, but what else also results? No, we've also broken the pi bond. So it doesn't make sense to call this strictly an acid-base step because we did break the pi bond. So this is a typo within my slides that I keep meaning to fix and keep forgetting. Okay, this is an addition mechanism or an addition mechanistic step. It's an electrophilic, at least according to how Carty organizes them, the electrophilic addition step, because we are adding a positively charged species, our quote-unquote electrophile. Okay, and I would almost argue that Carty needs to add another mechanistic step, an acid addition as opposed to an electrophile addition, and losing the pi bond. Okay, so it is best as an electrophilic addition, not as an acid base. Okay, so let's go back and take a look at this. So not acid base, we'll call that electrophilic addition. Okay, we had the other one as a coordination. Those people looking at this might be like, well, couldn't I have just as easily, and actually I'm going to change the orientation on this to make it a little bit easier to show, couldn't I have just said that the mechanism happens this way? The pi bond comes out, those electrons go there, those electrons go there. Now I do it in one step. Why do I need to show it happening in multiple steps? Because I'm ending with the exact same product. Okay, there's no real difference in the product here. Why do I have to go through and show this as two steps? Okay, well, ultimately, where that two-step thing is going to come from is experimental information. So deciding which of these two mechanisms that we've drawn here is more valid is going to come from experiment. Okay, which is a bit unfortunate, because now what we're saying is that we have to memorize somebody else's experiment. Okay, so I want to, before we address that, I want to pull back a little bit and be like, well, does one of these make more sense than the other? Okay, whoops. When we think about our reactions and our mechanisms, I understand where we're going here. We're showing these as general forms, okay? But remember what we said about the acid. The acid has to be a strong acid, like HCl, okay? Because it is HCl, that chloride is taking the electrons from the hydrogen, okay? Because it is stable. It's a leaving group. It leaves the hydrogen alone. Because it is a strong acid, that happens effectively instantly. Now go back and take a look at that mechanism you're showing down below. You're showing that that effectively immediately thing happen is only happening because the alkene is forcing it to. That already says this is probably a bad step. Okay? The next thing associated with it, you can be like, well, I could still modify the mechanism so that that is now not a bad step. What I will go through and do is break it first, and then I'll have it attack. Okay, so I will start my mechanism by doing H plus, H to Cl, and then I still have to write less, right? Okay, well, what would be the issue then that an organic chemist or someone who paid heavy attention in the last unit say about that mechanistic step? Well, that mechanistic step is now dependent on three independent species all interacting with each other. We've got a threesome, a ternary, and now I'm all sorts of discombobulated, termolecular reaction, and the odds of a termolecular reaction happening very, very, very low. Okay, so low that it doesn't make sense to show as a mechanism, which means we just fired off a whole bunch of attempts at this, and we already have direct evidence based off of our understanding of how things work to say the bottom mechanism doesn't make sense. It's really just the top one. But again, ultimately, where this is going to come from is experiment. Okay, we have to get experimental evidence to support this, and one of the big experimental pieces that we see is that our rate is dependent on our acid, and that we see some subsequent other steps, and in particular that when we go through and look at our product, in very particularly carefully designed scenarios, we can see where the A- aligns. And what do I mean by that? Well, take a look at your product. Your product has a very interesting spot going on with it. That carbon is a chiral atom. Okay, why does that become problematic? Well, if we have a chiral atom, we had two potential ways that the A- could have come in and attacked, either from the top or the bottom. And sure enough, that's what we end up seeing. Okay, for those of you being like, but the pi bond back at the beginning could have attacked from the top or the bottom, so we could have ended up with it there too. You're right. Okay, and that's where recognizing the rates of these reactions and what species were involved in it also plays a role. Okay, the last thing that's also going to come in there is that we could bring in a hydrogen as deuterium, and we could notice that deuterium and our A- are not on the same side of the reaction. They would be on opposite sides or the same side. Okay, so all of those possibilities come together to really tell us that yes, indeed, the mechanism as shown here is the correct mechanism, and this is the one we're responsible for. Okay, so some kind of terminology here. The overall reaction, if we were to write that out in extremely tiny space here, the overall reaction would typically be written something along these lines, and it helps if I don't invert the structure. Not chloride, sorry, A. That would be our overall reaction. Okay, it's an addition reaction due to the loss of the pi bond, and this is what helps us to predict the product. Okay, so we can use that pi bond to predict the directionalities. Evaluating the structure and the mechanism is what forces our stereochemistry, and that predicts our regiochemistry as well. Where did H and A go with respect to each other, both in space and numerically on the molecule? In this particular structure, the molecule was very symmetric, so we don't really see that regiochemistry system pop up yet. Okay. The next thing I'd like you to be able to go through and do is to also look at an energy diagram. So here we've got our starting material. This one's a little bit more specific. Provide the mechanism of 2Z-butene with HBr, and then go through and provide the energy diagram. So again, take a second to pause, hit the space, click in the picture, make the movie stop, so that you can go through and show that mechanism. Okay, now I'm going to go through and show it. We're looking at our HBr. You'll notice that I'll add that bond. The electrons of our pi bond go and react with the acid. The bromide kicks off. The result is I've added that hydrogen, and I now have a carbocation, and I'll show that in red. Depending on your personal taste, you can show that hydrogen or not, because it can be implied. Okay, and it typically is. One of the problems that you might encounter is that if you're doing this in smart work, and I'll fix that in a second. Okay, if you were drawing this in smart work, oh man, fine. Let's be nice. Just to maintain the alignment of what our product is. If we were going to draw this in smart work, if we went through and showed this hydrogen, we would also have to show the other hydrogen that was starting there. Okay, so if you decide to start showing hydrogens, you have to show hydrogens on that position. Okay, so this would count. That middle structure, our blue boxy area, would count as a valid structure to draw, even though hydrogens aren't shown everywhere. Once you've shown them attached to a carbon, you must specify all hydrogens on that carbon. One thing I'll note as we're talking about smart work, if we go back and look at our alkene, if you're going to draw an alkene, smart work is going to have a hard time grading this one, particularly as cis or trans. If you want to specify cis and trans, okay, or you're being asked to, you will also have to show those hydrogens. Some of you may have encountered that issue with earlier homework assignments. You have to have those hydrogens on there so that SmartWork can go through and grade that. That's an artifact of the online system. Okay, so let's clean some of that up because we don't need the green and all that. Really all we wanted was our mechanism, and I don't want to see those hydrogens because they look messy. Okay, and so we now have our mechanism. Cool, so we'd want to go through and draw this. So I'm going to start this as reactant. That carbocation is an intermediate in the mechanism because it's not a formal product. And then we have our formal product. Okay, so if we start, I'm going to pick reactant kind of floating in the middle somewhere so that I don't have to exactly identify it. The intermediate is for sure higher in energy because of that carbocation. So I'm going to throw my intermediate up there. And then when I draw in my product has neither carbocation nor pi bond, so it should be lower than everything. I can now go through and draw my energy diagram where I connect, whoops, that was a little squiggle there, where I connect out my energy diagram, and now we're all good to go. We could reference the activation barrier, or the activation energy. We know this bottom part is thermodynamic controlled. And since I was writing too far away, started spelling wrong, and still spelled wrong, so clearly it has nothing to do with that. And then we've got our, our kinetic controlled, which is dealing with going up to that rate limiting step. Okay, and so now we've got our energy diagram and all's good with the world. Okay, if we wanted to look at a prettier version of the mechanism, here's our prettier version of the mechanism. Note that in my pretty version, I'm trying to be nice by showing you that hydrogen, and at the same time, I've screwed up because SmartWork would misgrade that. Okay, we need that hydrogen in there. Okay, so let's look at regiochemistry. We've got just a couple more slides before we finish this one out. What happens if we have an unsymmetric alkene? So we've got a bunch of alkenes shown up here, and you'll notice that they're all shown out with our products. And what we want to try and figure out is what they have in common. Okay, and this is what Markovnikov did. Markovnikov noted that our alkyl halide went to the more substituted position. Okay, or said another way, he noted that the hydrogen went to the less substituted position. And yes, we're now showing that bad. That's okay. Okay. And this is where you might hear people reference hydrogen as kind of a currency and say that the rich get richer and the poor get poorer, as in the carbons that had hydrogen get more hydrogen, and the hydrogens that didn't have hydrogen, or the carbons that didn't have hydrogen, get not hydrogen. Okay. And so this is what Markovnikov noted before a mechanism had been elucidated. Okay, and so that's kind of neat that he was able to make this observation. I do think it's a bit silly because that observation immediately comes from our understanding of electrons when we look at a resonance structure. That resonance structure predicts where our hydrogen is going to go. Our hydrogen, in all cases, because it's a strong acid, has to be H+, which means our hydrogen is going to go to the more negative carbon. So if you look at your structure and start to establish partial charges within that starting material, you can predict very quickly where your hydrogen is going to go, better than having memorized some silly rich gets richer nonsense. Okay, so again, my recommendation, follow resonance. If you don't want to do that because it's getting close to the end of the semester, you don't have that extra support network by being in person, then do what you got to do. You can start trying to memorize Markovnikov as a process to get through this. That will later come back and bite you. You should really be thinking about resonance as it applies to this. Okay. And almost the last slide, stereochemical traps. Remember how I said we would have to go to a reaction to prove all this? And I said that one of the things that we could do is insert a hydrogen, or insert deuterium instead of hydrogen. Because deuterium is still hydrogen, we are still looking at a strong acid. Because we're reacting with a pi bond, that pi bond could either react above or below the plane, okay? Which is what's going to generate, and of course I drew it backwards, generate two possible products with the deuterium below or the deuterium above the plane of that molecule. The bromide can then come in and react with the next reactive species, which is a carbocation, because it is a positive charge, and can also react both above and below, which then generates two potential products on that branch. We also get two potential products on the other branch. So if we go through and look at this, this single reaction generates four products. If we looked at the other mechanism suggestions, those other mechanism suggestions would not result in four potential products. They could get two products at best. Okay, so this becomes a better system or a better mechanism to explain what we actually see at the end result. Okay, so be aware of the stereochemistry of this. Usually you don't see stereochemistry pop up as a question here because the end result is that you get all possible stereochemistries. Okay. What could pop up is we could throw it at you and be like, which one of these things? And you'd be like, oh, it's that one. And you just select the first one you see. And one of the answer choices will be all of the above. Okay. So watch out for that. So here we go. We've got practice. There's a little bit of information in here that I want to call your attention to. You'll note that there is a box above this reaction to help you consider what you might need to get that reaction going. So again, I'm going to ask you to pause. What I'm going to go through and do is also pause, then I'll draw in all the answers, and maybe I'll discuss them if I think there's anything of particular interest. Okay, so again, click pause, hit space, because it's all just going to appear here in a second. So here are all our answers. So let's go through. Hopefully the first two were okay and you didn't have any problems with those. I did throw in a question here. Which one of those is correct? Hopefully you can remember from Unit 1 that those are the identical structure, just a three-dimensional rotation of each other, so it doesn't matter which one you specify. When we move down now to that purple one, our third one down, I again threw in the question, and you might be like, well, but again, these are the same, but they're not the same. That bromine is connected at a different position. Okay, so why would we pick black over red or red over black? This is again going to have to do with our mechanism in identifying that regiochemistry. Okay, are we best to have a partial negative, partial positive, or are we best to have a partial positive, partial negative? Then this becomes a challenging one to differentiate because they both have the same substitutions. But we also have the pi bond over here, which could resonate to stabilize a carbocation. So that resonance stabilization of the carbocation intermediate is what drastically drops the energy of the intermediate, with the positive charge being located internally. And they're both internal, but put the positive charge there, which means our leaving group, our hydrogen should go out to the other position. Okay, so what does that mean? This carbocation is our intermediate, becomes more stable, and the black one is our primary product. So when we're thinking about looking at those internal stabilities and assigning those partial positives and negatives, you have to ensure that you're also considering resonance in your answer. As we move to the upper top one where we've got an OMG, we'll look at this one in a little bit more detail, but I need a lot more space to draw products, which is why we've got the OMG. If we look at kind of the simple aspect of it first, Our hydrogen and our chlorine, there is no real difference there. We don't have a resonance effect, so we could just attach the hydrogen or chlorine wherever we wanted. Okay, if we decided to attach the chlorine where I did, it's wedged up. But didn't I say it could be wedged or dashed down as well? You'll notice that we didn't evaluate that in any of the other systems. Well, why not? Okay, the big reason why not is that there weren't chiral atoms in those other systems. So what I'm about to go through and do in just a little bit is I'm going to fix all of our reactions to ensure that they show the proper stereochemistry if it is necessary to show, because I fudged that and didn't really put that in when I needed to. Okay, so before I go through and do that, let's take a look at our last reaction. Our last reaction, the nucleophile in this case is going to be OH, is the oxygen found in water. You might say, but H2O is not a strong enough acid. You would be correct. That's why you need to add a strong acid. H2SO4 is a strong acid, generates a non-nucleophilic sulfate. Because it is non-nucleophilic, all it can do is donate a hydrogen to the structure and leave a carbocation. That's where water can act as a weak nucleophile now with an uber electrophilic species, because it's formally positive, and actually do our coordination for that last step, which we will see, I believe, in the next video. This was kind of a lead-in for that. Okay, so here I'm going to go ahead and pause and fix the stereochemistry. Feel free to go through and fix the stereochemistry as you see fit and ensure that it matches mine. So back at it, starting at our lower we'll start at the upper left. There's no change to that drawing because there's no chiral atom. As we go out, these two positions are the same, which means there's no need to show wedges and dashes. When we move to the next one down, yes, we have a chiral atom, so we should be specifying stereochemistry, so wedged and dashed. If we continue down, we have stereochemistry again at that position, which means we should be showing it wedged and dashed. A lazy way to get through this would be to just say plus enantiomer. Okay, because if we look at the above, the relationship between those is that they are enantiomers. So we have a nice cop-out for it. We could just write plus enantiomer. As we move to the upper right-hand corner, we run into a problem again. We talked about that stereochemistry. We can say, plus enantiomer. We can't say plus enantiomer here. That is actually wrong. So that purple structure would be, double-headed arrow. Dang, that was a bad idea. Is where we're showing, okay, now seeing those green carbons come in on the purple structure, that position may have flipped, but the other position, which I'll color in red, did not flip, which means they are not enantiomers. These are diastereomeric pairs, not enantiomers. So we can't use the term plus enantiomer. The red one, why the red ones? Well, we said the hydrogen and the chlorine could come in at either position because we're looking at partial positive and partial negative, or it could have been partial positive, partial negative. Because they were both secondary positions, there was no real differentiation, no resonance to contribute that. Both of those come in as potential options. As soon as we go through and draw that out, though, hopefully what we'd see for these red ones as an intermediate, we would get a carbocation right here. And like we talked about with our SN1s and E1s, as soon as we have carbocations, we should be considering rearrangements. Is there the potential to rearrange? I could take that hydrogen and, make a tertiary carbocation. That tertiary carbocation can now react with the chloride, and we'd end with the blue structure. So this single structure, which was intended just to test that enantiomer issue, just saying, hey, can we call them just enantiomers? No, we can't. Added a whole nother layer of crap behind it because it addresses the regiochemistry issue for products with red, and it also addresses that we have an issue with rearrangements as a possibility with our our electrophilic additions as well, under acidic conditions, because we have a carbocation. So just like we said in the last unit, when you see a carbocation, you better be thinking rearrangements. Okay, so I let that one kind of sneak up on you. Sorry, not sorry. Okay, with that, we'll go ahead and be done with this particular video.